You might have heard about the AWS outage that happened on the 19th and 20th of October 2025. Maybe your favorite application was down on that day. My job today is to explain what happened and how this brought down half of the internet. There is a postmortem that was released by AWS. It's a slightly dense document and may not be easily digestible for everyone, so I would like to break things down in a manner that you would find enjoyable. However, before we dive in, there's a few concepts that I would like to clarify, and apologies if this seems repetitive for people who are already familiar with this concept, but I just need to get this off my back. First is DNS, which stands for domain name system. Its responsibility is to translate domain names to IP addresses. So IP addresses are like the identifiers for computers or servers on the internet. However, IP addresses are a bunch of numbers that are really hard to remember by regular folk like you and I. Hence, domain names is what is typically used. So we would write google.com or facebook.com instead of the IP address. Now that we know that, within the AWS architecture, they have a DNS which is called Route 53, and this DNS is updated by another component called the DNS planner. This DNS planner's job is to come up with different plans. Think of a plan as just a snapshot of different domains and the IP address that should be mapped to that particular domain. And in this case, I've created 3 different plans, 1, 2, 3. Then the planner has a bunch of enactors. We can think of the planner as a boss, while the enactors are workers that take those plans and apply them into the DNS. So the fundamental issue that happened is that DynamoDB, which is a NoSQL database that powers a lot of AWS services, has a domain name. However, there was no mapping of that domain name to the corresponding IP address. And consequently, what happened is that every application which used DynamoDB, either directly or indirectly, couldn't reach the database because it couldn't find the IP address for that particular database. Now, I would explain how this came to be. The reason was a latent race condition. And here's the scenario. This is an overly simplified scenario. It's probably more complex than this, but I think this really captures the essence. A disclaimer also, I do not work at Amazon, so I do not know the exact structure of the data, but this is information that I have inferred from reading the postmortem. So assume we have this DNS and the initial state looks like this. There are many different domains, but I've simplified it by choosing just one domain, which is food.aws.com, and this is the corresponding IP. And there's also some metadata around the exact plan that is responsible for creating this DNS record. So enactor A starts executing plan 1, and in order to prevent other plans from overwriting what it's doing, there's a locking mechanism, and this locking mechanism is per DNS record. So it requires a lock for food.aws.com. However, at the same time, enactor B tries to begin plan 2. And attempts to acquire the lock for foo.aws.com also. However, it is blocked because enactor A has not finished executing its plan. So it goes into a blocking state. At a later time, A finishes updating the DNS record. As you can see, the DNS record is now 137. And the final state is that after it's updated DNS record, it tries to delete any stale records. In this case, stale record means that the plan is less than 1. Okay, but obviously there's nothing to delete here because this is the latest record. So here's the catch. Even though B tried to acquire the lock earlier and went to do a blocking state, there is no guarantee that the moment A releases the lock after updating the record, that B would be the next to get the lock. B still needs to contend for that lock with other instances of the enactor. And it so happens that in this case, enactor C woke up, tried to enact plan 3, and acquire the lock before B, which is still in a waiting state. In this case, C goes ahead to acquire the lock for foo.aws.com and updates the record. And notice that now the record is 157, which we can see from the plan up here. And the source of that plan, or the plan ID rather, is 3. Then it releases the lock after updating the record, and B finally has access to acquire the lock for that record. Then it updates the record, but at this time the record already contains plan 3, but B still assumes, well, I'm the latest plan, and updates it to 147 plan 2, which obviously is what is stated in its plan. Then it tries to delete any older records, but again, there's nothing to delete because there are no records that point to plan 1 or plan 0. Then C, at a later time, executes the final statement in its instruction set, which is to delete the old DNS records. That is, records which have a plan that is less than plan 3. And in this case, since B had updated the DNS record to become plan 2, C thinks, oh, this must be old, so I have to delete it. And it goes ahead to delete it, which leaves the DNS in an inconsistent state. Essentially, it became empty. So there is no record for foo.aws.com, and the DNS cannot translate foo.aws.com into any relevant IP address. So to summarize the fundamental issue, is that in between the time that an enactor starts enacting its plan and when it updates the record, the state of the system could have changed. Okay. There are two possible solutions that we can explore, because we can just speak about the problem and provide any possible solutions. One thing we could have done, or rather Amazon could have done, is instead of having these enactors simultaneously try to apply their plans, they could do it in sequence. But as you've already guessed, this could be a challenge because as the postmortem mentioned, they're dealing with hundreds of thousands of DNS records, and this needs to scale. So doing it sequentially might not be the best option. Another thing that they could have done is to explore an optimistic lock-in solution. Essentially, in this case, whenever we're executing a statement to update a DNS record, we need to add some extra checks so that the particular record is only updated if the plan we are trying to insert is greater than the plan that the current record points to. In this case, I'm using MySQL syntax. I do not know what database or storage mechanism is being used for the DNS, but I've chosen this to illustrate the idea that I have in my head. So as you can see, if you're familiar with MySQL syntax, we can insert we can perform an upset, not an insert, of the domain, the plan ID. This is a typo. It should be plan ID first before IP. Anyway, and we ensure that if the plan ID that we're trying to insert or upset is greater than the previously stored plan ID, that is only when we update the IP. If it is less, then we essentially ignore that update. And if this was done, then this second update would have been ignored and the system would have been left in this state. Well, I hope this was helpful and this gives you some insight into the outage. Please feel free to dive into the postmortem. I would add the link to the description of this video. Have a great week.